Welcome. In this lecture I will start introducing the ideal MHD equilibrium solutions, and so I'll introduce some basic concepts of force balance. I'll look at some simple example of an equilibrium in a slab geometry, so we just have a flat situation where everything has no boundaries and it's just infinite size. And then I'll look at the concept of magnetic pressure, which this introduces. So we're going to look at ideal MHD. So we have the equations I'll just put down here. So we have d rho by dt as this is the density. So and then we have the u dot grad rho. So this is the mass density equation. We have the momentum equation. In each case here we have the advection derivative. And here we have the pressure force. So I put the density here on this side. Example, so this is the momentum. Now we have the pressure force, and we have a J cross B force. This comes from the electromagnetic forces on a conducting fluid. So we have a current being carried by the fluid, and it's sitting in a magnetic field, and that creates a Lorentz force. And then we have finally the pressure equation. I have ratios per heats, P, and then a divergence, so a few here. And then the auxiliary equation we're using is Ampere's law. So we have curl of B gives us mu naught J, and then the magnetic field is evolved in time with this dB by dt is curl of V cross B, or U cross B. So the induction equation gives us evolution of magnetic field. The Ampere's laws give us current. And then J cross B gives the Lorentz force. And this is a closed set of equations, so the ideal MHD equations. And now we're looking for stationary equilibria. So in general there can be equilibria where there's flows where U is not zero, but here we're looking for stationary equilibria. So stationary here means U is equal to 0. And equilibria just means it's in steady state, so d by dt goes to 0. And so most of these equations will now go to 0. So all the time derivatives go to 0. And here, because we've assumed stationary as well, then this term, like most of these terms will go to 0. So everything involving u goes to 0. You can start to see that most of this all vanishes. And so most of these equations all cancel out, and the only thing that's essentially left over is this bit. So we have this bit here. So we have, this is force balance, so pressure forces balanced by Lorentz forces, and then this Ampere's law relates the magnetic and the current, magnetic field to the current. And so the basic equation for force balance in an ideal MHD plasma is just that J cross B is equal to grad P. And most of the examples, all the examples we look at in many different geometries, so in slab geometries, cylinders, and tokamaks, so toroidal geometries, all essentially different ways of writing this, because there are many different ways you can have current profiles or magnetic field shapes, and so this equation actually has a huge number of different solutions, even though it looks quite simple. Okay, so we're going to start with a slab geometry. Okay, so there's a couple of consequences of this equation which we should go through. So first of all, this is a cross product, and so for some very simple ones, I just take the dot product of this equation with J, for example, or with B, and so you can immediately see that, so B dot J cross B, that's just identically equal to 0, and that's equal to B dot grad P. And so this means there's no pressure gradient along magnetic field. Or equivalently, the pressure is constant along magnetic fields. No pressure gradient along B. So pressure must be constant on magnetic fields. And similarly, we can also dot this with J, so to say that J dot grad P is also equal to 0. So there's no current in the direction of the pressure gradient. So current p direction. Okay, so we'll start by looking at a simple geometry, so just a slab. So here's a 2D solution, so we have a y direction here, and we have an x direction like this. And we imagine we have a pressure gradient which is just up, so grad p is that way. So grad p is basically proportional to y. Okay, and then we have a magnetic field in the x direction, so b is just bx in the x. So I'll use hats for this unit vector in the x direction. And we can see if there are any solutions to this j cos b is grad p with this geometry. So imagine here this is just an infinitely long geometry, so b field is constant in x, and it potentially varies in y. So bx could be a function of y. Grad p is also constant in x. Okay, so what we have here, so we need the j cos b is grad p, so we need to work out j. So j is 1 over mu naught curl of b. If you write down curl, this gives us the various components. So this is jx is 1 over mu naught. We have a db y by dz minus dbz by dy. Now by and bz are all 0, so these are 0. And we have jy, and that's just 1 over mu naught. So we have dbz by dx minus dbx by dz. So d by dz is 0. So nothing varying in z, so z is into the page and everything is constant. So that goes to 0. bz for here is 0 as well. So this is all also equal 0. And then we have jz, and you have 1 over mu naught, so dbx by dy minus dby by dx. Now b is not changing in x, so d by dx is 0, but we do have this term here. So this term is potentially not 0, so this is just 1 over mu naught dbx by dy. Okay, so we have a current which is in the z direction, so we can draw this in here. So we have so j is j in the z direction. This b is just in the x direction, and pressure gradient is in the y. And so now we can work out the j cos b force. So j cos b. So this is the jz component. So 1 over mu naught dbx by dy. So that's in z. So then we multiply this by b. So multiply by bx, and now we have a z cos x, and this is minus y. So these are all unit vectors in the z, well, x, y, and z directions. Okay, so this we can start to manipulate a little bit. So this part here, this we can write down as this is d by dy of bx squared over 2. So if you just do this by chain rule, you get back this expression here, and so we can write that this is, so we have minus d by dy of bx squared over 2 mu naught y, and this must be equal to the pressure gradient. So this is equal to dp by dy, which is in the y direction. Okay, so then we have we essentially group these together. So we have d by dy of pressure plus this pressure here. So this P is the plasma pressure, just the fluid, and plus Bx squared over 2 mu naught. And that's equal to 0. So what this says is that if you have pressure varying in the y direction, then the magnetic field strength varies in the opposite sense. So if P is increasing up the page, so if I draw this diagram again, so we have this is the x direction, that's the y. So grad P is up, so we have high pressure here, and we have low pressure underneath. Then the magnetic field is going in the x direction. It's B is this way, and this says that if P is increasing up the page, then B must be decreasing up the page. So we have decreasing magnetic field, increasing magnetic fields. So we have a strong magnetic field on the bottom and a weak magnetic field on the top. And this is essentially a balance between two pressures. So there's the fluid pressure, and then this is called the magnetic pressure. And you'll see that this is an important component in more complicated geometries as well. This idea that magnetic field has a pressure. So we'll see this several times. Okay, thank you.